So welcome everyone. This is Ivan from EPIC, the European Photonic Industry Consortium, and we continue the series of our online technology meetings today with an event dedicated to satellite quantum communications. And we have a wonderful possibility to talk to 6 key players in the industry of satellite quantum communications today. We have Laurent de Parny, the quantum system engineer at Thales Alenia space, Emmanuel Fretel, presenting from AUREA Technologies, Nicephore Nicolas, business developer at iXblue, Malcolm Humphrey, the CTO of PLX, and Martin Wölz, the product manager at Jena-Optronik, and Costantino Agnesi, scientist and product developer at ThinkQuantum. So I expect a very intense event today. This will be a great discussion. And let me also present the audience today, because in the audience we have representatives of almost every chain of the value chain in satellite communications. We have people developing advanced materials, the software to analyze the images. We have market intelligence and consultants, people who work with single photon sources and single photon detectors, developing optics, electronics. We have system integrators, and last but not least, we have end users of these technologies. Besides, the event today is supported by our 3 sponsors, ficontec, EuRA, and PLX. And I'd like to invite the representatives of these companies to say a few words about their companies. First, Malcolm Humphrey, could you please introduce PLX?
Good morning, everyone. Welcome. So PLX is a precision optics company. We do alignment systems, bore sighting systems, any precision optics for any environment, from space down to gravitational wave experiments. We do optics for all those harsh environments. So anything precision, plug and play optics, that's us. So we hope to contact some more companies in this area and start doing some interesting collaborations.
Thank you very much, Malcolm. We have also ficontec, and I believe there is someone representing ficontec in the audience. And because if not, I will just say that ficontec provides device microassemblies and testing solutions for the photonic industry. And the solutions are realized as cutting-edge and high-precision production systems, utilizing advanced automation approaches, and regardless of the device material and target application. And the third sponsor of today's event is EuRA. The EuRA is an international consulting company for innovation and technology. And EuRA consultants support companies, research institutes, and municipalities of all sizes in enabling technical innovations. So we'll thank again the sponsors of the event. And let me come back to the agenda of the event. The first speaker for today will be Laurent de Parny, quantum system engineer at Thales Alenia Space. Laurent, please, whenever you're ready.
Yes. Hello, everybody. I'm ready. So I will share my screen. Okay. Okay. So you should see my screen. Can you confirm you see my screen now?
Yes, we're good.
Yeah, so thank you very much, EPIC, for the invitation. I'm Laurent de Parny. I'm working at Thales Alenia Space as a system engineer, and I'm working in a quantum satellite communication. And so just a few words about Thales Alenia Space. So we belong to the Thales group. So Thales Group is a huge group over everywhere in the world, and Thales Alenia Space is in charge of we are the satellite providers for the Thales Group, and we are involved in many satellites projects, and particularly in the framework of this discussion, we are involved in many projects related to satellite-based quantum communication projects. So a few words about our roadmap. So we are involved in two kind of projects. So let's say there is two families. There are two families of projects we are working on. So the first one is a quantum key distribution project for the safety of Europe. And the other one is quantum information networks, so QEN. So this is typically the basics for the quantum internet or quantum networks of quantum machines, more generally. So we have many ongoing projects related to QKD. So we are involved in the Saga project, for instance. So maybe you know that Europe is concerned about the safety of communications, because you know that there is a threat because of the quantum computer, which will be able to break encryption, like the Rivas Shaman Adelman. So this is RSA we are using on the internet, and so this is a big problem for our communications. And so Europe is an initiator of a project which is called EuRA-QCI, the European Communication Quantum Infrastructure. And we are involved in this project, and Saga is related to this project, but this is the space part of this project, and this is driven by the European Space Agency. So we are working for European Space Agency, also for European Commission. We are in this project, we are speaking about low Earth orbit satellites and also geostationary satellites. We are developing building blocks. We are starting to work on the building blocks for quantum communications. So this is a ThinkQuantum project, and we are also involved in R&D projects to develop quantum sources based on entanglement, and also more generally the network, the quantum information network. So as I said, we are working on two families of projects. So the first one is quantum communication, quantum key distribution for quantum cryptography. And what we want to do, the service at the end, is to share random numbers, random bits. So this is classical bits. At the end, this is 0 and 1 in a random way. So this is random 0 and 1. But we are using quantum physics to establish symmetric keys. And this is robust. If you think about the threat of the quantum computer, this method is perfectly secured if you think about this kind of threat. And we are working on another project which is sharing the quantum resource in order to put in a network many, for instance, quantum computers or quantum sensors. And for those who are working on, you know that there is a problem. You cannot use just fiber-based networks because you cannot amplify the signal. If you amplify the signal, you destroy the quantum bits because they are very weak by nature. And so the range is limited on networks. And so for quantum key distribution, we are using trusted nodes to increase the range of the network. And so, in fact, it's natural to think about using a satellite to connect ground users, because the satellite can have a very extended range. And in fact, the losses appears mostly in the atmosphere. So in the 10th kilometers, close to Earth, to the Earth. And so So there were many very interesting experience made by Chinese people with the satellite misuse, and they show that one can use a satellite to perform quantum key distribution, and in fact many things like quantum teleportation also, and they did it in 2017, and now they have launched another satellite which is called Jena-1, and Jena-1 is specifically designed for QKD, and so we are using the satellite for this purpose, and we are developing designing quantum satellites for QKD at the moment. So to be more specific on what is a channel, so I will not speak about the network because I think for this presentation this is more interesting to discuss what is the emitter and the receiver. So we used to speak about Alice and Bob. We want to communicate securely. So here this is for QKD. And so typically one can consider that the source is on board the satellite, and we emit the qubits through telescopes, and it goes through the vacuum and the atmosphere, and the signal comes finally in a telescope receiver at the ground and goes into a detector, analyzer, and a time stamper. And then after we use also a classical channel to perform the sifting. So we need a classical channel to communicate some information and also to correct, because sometimes there is errors and you have to correct errors. And so this classical channel allows to do this. And so this is a quantum channel which is from space to the ground, and the classical channel is bidirectional. And what we are using to do this, we are using a laser source. So typically at 1950 or 800 nanometers. In the encoder, we are using intensity modulators, and of course also optical fibers, connectors. One can encode the information into the polarization of each qubit, of each photons, emitted photons. And so to do this, we are using polarization controller or phase modulator. So there is many ways to do this. And typically also a variable attenuator and polarizing beam splitter. So this is just to give you an idea of what kind of equipment and component we are using. There is also quantum physics in the quantum random number generator here. We generate 0 and 1 in a random way, and this information is encoded into the single photons, and then this is decoded here at the receiver level. And so in this chain, we are also using telescopes, optical terminals. We called it because a telescope is static and optical terminal is a telescope that is moving. You have to track the satellite. And also adaptive optics and processors, of course. And one very interesting perspective is to use chips, photonic chips, to reduce the size, weight, and power. So in a satellite, this is very important to optimize the size, the weight, and the power, because you do not have infinite resource, of course, and infinite space. So this is for QKD. And then for the space-based QKD and quantum information network, these networks are based on entanglement. So for this kind of networks, we are typically using entanglement sources that are put on board the satellite. And so this is pairs of entangled photons that are emitted to the ground, to Alice and Bob, which are located at the ground. And the entanglement allows to perform many things. So you can extract keys, you can perform QKD with entanglement. And that's interesting because in this kind of setup, there is no keys that are stored on board the satellite. So the satellite is not a trusted node anymore. This is just an emitter of untangled photons pairs, and then we use the correlation, the quantum correlation, so the entanglement, to extract keys at the ground. But in fact, this kind of setup is also a building block for the quantum information network that is a network based on the entanglement distribution into space, into the space segment and the ground segment. And so here also we definitely need a laser source, of course, so a pump laser that is pumping a nonlinear crystal that will generate pairs of photons, and we can encode the information into the polarization or using a phase modulator and so on. So there is a list of components here at the right corner, and so as you know, this is a very everybody's speaking about entanglement because there is a Nobel Prize, and we have a French Nobel Prize, Alain Aspect, who did an experiment on the entanglement and showed that entanglement can be or quantum correlations that are that one can use this quantum correlation to perform keys, quantum keys. And there is also Anton Zellinger, who performed the first experiment of the first teleportation. And this kind of effects are now very interesting for us. We are in industry, we are very interested about this because one can think we can solve the service at the end based on this effect. And so I'm working in Toulouse, France, at Thales Alenia Space, and our group is growing. So this is definitely a very attractive topics, and we are hiring people, engineers who have a quantum background. And we are also very interested about collaborations with SMEs, small companies, or also big companies. If you have skills on this, that's very interesting for us. And so, thank you for your attention. And I will be pleased to, of course, answer your question.
All right. Thank you very much, Laurent. This is a very encouraging talk. So please, everyone, don't hesitate to push the raise hand button to ask the questions you may have for Laurent. I see actually there's already first question from Mathieu from INO, please.
Thank you, Laurent, for the interesting talk. I wonder, I would like to know, and it's a question that I ask to many people, especially in quantum information. What do you think about the possibility to use QKD or even quantum internet during, at any time of day, including when there is cloud? Because, with optical links, basically you cannot pass through clouds. So how about that? And how about, what is your thought about that?
Yes, thanks. That's a very good question. In fact, this service is not operating I mean, you have to first establish the keys, then the keys are stored, and the user requests keys that have been stored in a previous time. So this is not and how could I say this?
Yeah, but for the QKD, I can imagine that. But when we looking at the, putting into the entanglement two quantum processors, maybe one in Canada, like I am right now, and one in France, you will need some kind of a direct link for that. So how are you going to deal with that?
Yes, so how to deal with that? So for QKD, it's not a problem because you can establish keys, then stored keys, and ground user request keys, and they can have on-demand keys that have been established in a previous time. But for quantum internet, this is more challenging because what you can do is that you can establish entanglement correlation between users, but definitely you have to store this entanglement into quantum memories. So if you want to store a qubit, then you have to think about using quantum memories into this network.
Yeah, I know, but still, when you need a link, if you got a cloudy day, that would be a bit difficult.
Yeah, sure. So that's true. Huh? If there is clouds, you cannot perform an optical communication. So that's a real problem. So you have to think about a system that can operate not on demand to establish the resource. So you store the resource, you produce the resource. So the resource could be quantum keys. So when I say quantum keys, I mean keys established by QKD, or it could be entanglement which are pre-stored in quantum memories, and then the user requests the resource and get the resource on demand. So in these systems based on optical communication cannot work if there is cloud. So definitely that means that the systems is operating in a first step and generating the resource, and the resource have to be stored at the ground. And then when they are stored, when the resource is stored at the ground, end users can request whatever they want, so QKD keys or entanglement.
Okay, but so you can let's say you can postpone the quantum entanglement distribution, right, using quantum memory scheme.
Yes, exactly. So this is this trick. In fact, to think about a mission for this system, you have to think about who speak with who. So the ground telescope has to speak with the satellite, and so you drive the system in a way that you pre-stored the resource of interest in order to have the resource at the ground, such that end user can request and get the resource on demand at the end. So you pre-share, you pre-store all this resource.
Okay.
So you operate not in real time. So that does not mean that the end user requests to the satellite to send a QKD keys on demand. That's not that could not work in this way. So the end user only can request a key to a server, let's say, a memory. So we used to speak about a local key manager system, and the local key manager system for QKD has the keys stored, and then it can delivers the keys to the end users. So yes, to answer your question, this is not a real-time system, but this is pre-shared resource.
Okay, thank you.
Yeah.
It's great to see that quantum communication still raises so many questions and interesting debates. But on a little bit different note, Laurent, I was wondering, so you mentioned a few times that Thales Alenia Space is looking into collaborating with other companies, including SMEs, and you showed this list of components that you're already using. So can you maybe highlight which specific components you would be looking into obtaining from other partners, from external entities?
Yes. So in our project we have clarified who are the providers, and when you work for Europe, you want European providers. That's a strong request from Europe. And for instance, we are very interested to work with people who can sold us crystals, photonic crystals, nonlinear crystals, for instance, because so far there is a lack of providers of this kind of components. And also I have mentioned chips. So QKD chips is very interesting for us, and that could be major asset for us to have this kind of component on board our satellites. And so I can also say that, for instance, we are working with AUREA, who will speak just after me. And typically, we are very interested to collaborate with this kind of companies who are experts on untangled photon source or detectors, single photon detectors. So that's exactly what we are looking at for our projects.
All right. Yeah, because I believe there'll be multiple people in the room who might be interested in this kind of collaboration. So please don't hesitate to contact me or Laurent.
Yes. Yeah. We are also collaborating with universities, of course, with French experts on this. And I was mentioning quantum information networks, and so we are also very interesting about what is emerging in the field of quantum memories and repeaters, quantum repeaters, or entanglement swappers, let's say. And so far, this is they are mostly in labs, in research labs, but we know that there is French companies working on, and also in the USA. So we had discussions with very interesting companies. So, for instance, some of them are already. We had a discussion with a company who sells the first quantum memory, and that's very interesting. So we see that it is emerging in the market. So there is a need for industry to have companies who are selling this kind of equipment.
Okay. Thank you very much for the response. Is there maybe a last question for Laurent? Yeah, Pu Hyun?
Yes.
From Kai Labs, please go ahead.
Yes, thank you, Laurent, for the very interesting talk. I had a question beyond this project. What exactly is the business case for Thales in investigating this quantum QKD and quantum states, quantum internet topics?
Yeah, so for QKD, the wish is to work for the government, also for the security in Europe. And we expect that a market will emerge in quantum key distribution, and so we definitely need to be at the top level on this topic, because this is very important for the stability of the French economy and for Europe. And for the quantum internet, we expect that so we have a roadmap. We have published a roadmap in a paper. We have put it on archive, and so we explain what is our vision and where we want to. When we think we will go in the quantum information networks, and so we expect that there will be also a market, and so that's also important to be a primary industry working on this.
Okay, thank you.
Okay, yeah, but okay, for quantum information networks, it's very complicated to have a business plan, because this is very challenging, and we don't know when it will happen, but it seems that things are moving on, and we definitely are involved in this topic.
Okay, and on the QKD side, so does Thales plan to be an operator of quantum quantum key distribution service, or is it just a supplier of different components, different subsystems?
Yeah, so I am system engineer, so I'm not the good guy to answer this question. But my point of view is that we are working with operators like Eutelsat, French operators, and many operators. In fact, there is also SES in Luxembourg. They will launch Eagle 1. So this is a satellite for QKD. So what one perspective is to be a provider, because this is something we are doing at the moment. We are providers, satellite providers. But okay, I cannot answer if one day we will be also operator. So far we are working closely with operators, but I don't know. So this is a question for my boss, I will say.
Okay, thank you.
Welcome.
So thank you, everyone. Let's continue the discussion at the end of the meeting, because it's time to pass to our second speaker of the day, Emmanuel Fretel, the project manager from AUREA technology that develops several key components for a quantum communication. Please, Emmanuel, whenever you're ready, the floor is yours.
Yes. Can you see my screen?
Yes, you just need to go in the full screen.
Yeah, 1 second. Okay. So, thank you very much. Hello, everyone. So, I am Emmanuel Fretel, and I am the project manager on space activities at AUREA Technology. I would like to thank EPIC for giving me the opportunity to present AUREA activities during this online event. And I will introduce during a few minutes the products and the projects concerning space quantum communication activities at AUREA. So on the next slide, so AUREA is a 100% French company having more than 15 years of experience in photonics, and more specially designing, manufacturing, and selling building blocks for quantum communications. So we are located in east of France, in Besançon, close to the Switzerland border. And our team has greatly experienced people in quantum optics and photonics. And we are one of the worldwide key players working on quantum communications products. Being a 100% French company is essential for quantum communication projects, because European sovereignty is necessary to secure health, financial, military, and so on sensitive data. And we expect a fast-growing market in the coming years about terrestrial and space quantum communications. So on the next slide, you can see our key building blocks products for quantum communication. These products are already available at AUREA. And in the past, a couple of years ago, we decided to work at the 1550 nanometer telecom C-band wavelengths for the QKD application for several reasons. The first one is to be compatible with the existing telecom infrastructures. The second is to use a standard well qualified telecom components. And the last one is to develop, and this is very important for us, very compact, convenient, and robust products. On the left part of the slide in red, you can see our current terrestrial product line using QKD systems. So the first one is the entangled photon source, working with the polarization entanglement. The second one is a single photon detector, and the last one is a time correlator electronics to detect the time arrival of photons and to make the time correlation between photons. And on the right side of the slide, on the blue, you can see our new entangled photon source for the space application, and I will discuss about it later during the presentation. So the dimensions of all these products are about 10 to 20 centimeters. This is very small boxes to be very convenient for the user. So in 2021, during the G20 organized in Italy, in Trieste, we did a demonstration of QKD between Italy, Croatia, and Slovenia. And this demonstration was performed by using some AUREA technology equipment with some partners. This demonstration was possible thanks to the choice of the 1550 nanometer telecom wavelengths and the existing infrastructures, but also to the proximity between the cities involved in the project. But it is not possible today to transmit quantum keys based on entanglement in optical fiber over distances higher than about 150 kilometers. And this is why it is very important to overcome this limitation by using space quantum communications. So in the frame of the Saga project, the one Laurent told us just before, AUREA has been working about a new high performances entangled photon source demonstration model. This project has been funded by the European Space Agency with the support of the French National Space Agency, the CNES, and in collaboration with our partner Airbus Defence Space for the space compatibility assessment. So the main requirements of the agency were the following. They asked us to develop a compact and robust module at 15 nanometer telecom C-band based on the time energy entanglement, not on the polarization for CIS1, on the time energy. The telecom wavelengths allows to benefit of a large space heritage based on optical telecom components for the space segment, but also for the ground station quantum receivers. So this is also very important because we are working on the satellite side, but also on the ground stations. And the agency also requires an efficient transmission link with a secure key rate of at least, let's say, 10 bits per second in a low Earth orbit scenario. The time energy entanglement allows us to have very high rate of photons, up to 1 gigapair per second. And this makes the time energy encoding a good candidate for space quantum communications. And finally, they ask us for a full day, for a daily operation between day and night, which is also required, and this is compatible with the 1550 nanometer wavelengths. And this feature is essential to distribute keys almost continuously to end users. And this is more complex and almost impossible at other wavelengths closer to the visible range of the spectrum. So we have developed a laboratory model and do a demonstrations to the agency recently, and we presented the results during the IXO conference in Dubrovnik in Croatia in October 3 weeks ago. So this is on this slide, you can see the main feature of the new 1550 nanometer time energy entangled photon source developed by AUREA technology. It consists of a compact all-fiber optical architecture, making it very robust for the space environment when compared to the free space bulky systems. So the mass of the entangled photon source is less than 2 kilograms only, and we have a very low consumption, less than 15 watts, and very low thermal load. And the dimension of the entangled photon source, the time energy entangled photon source, so is only 10 centimeters by 10 centimeters by 20 centimeters. This is a very compact one. And all these features make our source an ideal candidate to be embedded on board of a quantum communication satellite. So on the picture, on the bottom of the slide, you can see a full QKD optical bench based on the PPA92 protocol, including the photon source on the right of the picture and the receiver module at the center and at the left of the picture. These receiver modules can also be integrated in the future quantum ground stations. So to conclude, on the last slide, we have developed a new high-performance system energy entangled photon source at 1550 nanometer on its quantum receiver modules. And our modules are ideal candidates for space quantum key distribution applications. So if you are interested, we can provide you a full demonstration setup to start to work about QKD in your laboratory. And we accept the next steps for AUREA will be to develop an engineering qualified model and then a flight model in the coming years. And we also target to make an outdoor free space demonstration with our quantum building blocks to perform a quantum link outside. So if you are interested to collaborate with us, you can please don't hesitate to contact me at space@aureatechnology.com. And that's it. Thank you for your attention.
Thank you, Emmanuel. This is a very interesting presentation you gave. Is there any question for Emmanuel? I was actually wondering myself, Emmanuel. You were talking about these sources of entangled photons, and so single photon sources. And of course, the quantum networks are fully encrypted if your source is a single photon source. But what if you emit several sources? How quickly you lose the encryption in that case?
Oh, that's a good question. So,
well, let me put it this way: how reliable is having this single photon source from AUREA? Does it allow the full and reliable encryption, or?
I'm not sure I understand the question. So, just with our source, we provide photons.
Is there a possibility to emit several photons instead of one, or is it really reproducible emission of single photons?
Now we produce entangled photons only, so with some randomness. That's it. In the time energy entangled photon source, we have two quantum variables which are very random. We emit photons randomly in time, which is one random process to make the quantum key distribution process. And we also produce photons randomly in energy or in frequency or in wavelengths, which is equivalent. And this makes the second variable we can encode with our time energy photon source. And we use these two entanglements to provide the QKD and to make the quantum key distribution from the satellite to the ground station.
All right. Yeah, I understand. There is also a question in the audience from Jesse from ThinkQuantum. Please go ahead.
Hi. So I have a question. Well, actually, earlier this year, we delivered a SNSPD system to AUREA technology. So I actually wonder if you're going to use SNSPD for this mission, or probably APDs. So what type of detector are you going to use?
Yes, for sure. For the terrestrial application, you can use avalanche photodiode, but for the space application, today it's necessary to use SNSPD detectors with the cryogenic detectors ones, because they have better sensitivity compared to the current avalanche photodiode, for sure. And they have better noise and better quantum efficiency, even if they have a lower speed to detect the photons. So
Thank you.
Yes, we're using SNSPD, definitively.
Thank you. Yeah, if I may, so also I'm guessing, are you going to couple the photons from the telescope into a single mode fiber?
Today we use a single mode fiber to do the coupling of the photons to the detectors. Yes, we don't use the telescope for our demonstration. We are not in the free space optics. We did the first demonstration to the agency by using optical fibers and optical variable attenuators to simulate the losses on the transmission link from the optical source to the detector. But yes, we use a single fiber to do that, and it is very important because the SNSPD detectors are more or less sensitive to the polarization of the incoming photons, and we have to maintain the polarization between the source and the detector. So we don't work with a multi-mode fiber to do that.
Okay, thank you.
Another question from Martin from Quantum Technology Laboratories.
Yes, hi. Thank you very much for the nice talk. I also have a question regarding the detection. So if you want to implement it from the satellite with a LEO passing quite rapidly, how would you actually do the measurements in terms of the Franzen interferometer you need? So would you necessarily need to couple into fibers, or would you like to do this free space?
Yeah. So first, there is no interference. Thanks to the design of our source, There is no interferometer inside the satellite. Everything is on the ground station, which simplify a lot the development and the development of what is on board of the satellite. So that is very important to understand that. So we need two in-balance interferometer on the two ground stations, and that's it.
Okay, then I would like to comment that this is extremely difficult, and we have done this over a 10-kilometer free space link, a static free space link, and it's very hard to achieve it. So I'm really wondering how you want to implement this from a satellite on ground. I obviously understand this.
Yeah.
Did you already do some field tests? This is my question.
Yeah, we have some filters, yeah, of course, yeah.
Over free space?
No, everything is fiberoid for sure.
Okay, good. Then
we don't use AUREA technology. We don't like to use free space optics. Everything is fiberoid. Okay. So for the filter and for the unbalanced interferometer. But because it's more robust, it's more simple to use.
Okay, but
and we have to stabilize it with. We have to stabilize the interferometers by having a very stable temperature.
Mm-hmm. This I understand, but then still the claim is that this source is developed for a satellite communication, and you think this will work?
Yeah.
Okay. Good luck.
Yeah. Okay. Thank you.
Okay.
Thank you, Martin, for the question. And the next one from Farzan from Siena.
Yes, thank you so much. Question I have is with regard to your wavelength selection for your source. I'm wondering, why did you choose 1550? 1550 is a good low loss window for fiber, but why did you choose that for space communication? My understanding is that people usually use the 800 nanometer band for space communication because of the loss. So why did you use 1550?
There is many reasons for that. So the first one is because it is technologically speaking, it is simpler to develop a very compact and very small and very stable and robust optical architecture. So this is one reason. The second one is it is almost impossible to make quantum communication day and night, and especially during the day due to the noise of the sun. Sorry, at 800 nanometers, at 1550 nanometer, we are less sensitive to the noise due to the sun, and it is possible to have a day operation for the quantum key distribution. And this is due to the fact that the detector is less sensitive to the sun at 1550 nanometer when compared to the 800 nanometer. And this is very essential because the agency asks us to have a daily operation for the quantum key distribution. And there is some other minor reason for that, but the main reason are these two ones here. Technologically speaking, it is simpler, and we are less sensitive to the sun noise.
Do you have any issues with the loss in the atmosphere in that wavelength, or not? Comparison to 800.
The transmission at 1550 nanometer is a little bit better when we compare to 800 nanometer. Yes, there is about a factor of 2 in favor of the 1550 nanometer wavelengths. The Raman diffusion and the Rayleigh diffusion is better at 1550 when compared to 800 nanometer, but the beam divergence is better for the 800 nanometer. Okay, and so Thales Alenia Space made some trade-off about that on some analysis, and the other space integrators did the same analysis, and nobody knows today 1550 nanometer or 80 nanometer or 800 nanometer will be better. But what we saw in Dubrovnik that every companies, maybe except to Austria, are going, and Germany, so Austria and Germany are going down to the 1550 nanometer wavelengths because the trade-off shows that it will be maybe a little bit simpler to integrate these wavelengths in the satellite.
Very well, thank you.
All right, Matteo, the last question and very short one, please.
Yeah, very short question. It's one for one of us. Is it really the best wavelength at 1550? Did you look maybe to go further at 2 microns or 2.5 microns?
No, I don't. We don't do. I never see analysis at higher wavelengths about that. I don't know.
Okay, thank you.
Yeah, and the problem that we need the detectors. So
no.
Yeah, but there is solutions that you are developing right now in France.
Yeah, and
up to 5 microns. So
yeah, but typically the good windows for the sorry, I just a few.
No, it's okay.
The good windows, atmospheric windows, are close to the visible one, so 800 nanometers and 1550. There is also 164 nanometers. So Germans have worked a lot at this wavelength, but now discussions are around 800 nanometers or 1550.
Okay.
Yeah, typically the trade-off is close to these two wavelengths for I mean for space to ground applications.
Okay, good. Thank you.
Yeah, welcome.
All right. I suggest that we will continue our discussion at the ramp session at the end, because I cannot wait anymore to introduce our next speaker, who is Nicephore and Nicolas, business developer from iXblue.
Hello. Hello, everyone.
Welcome, Nicephore, and yeah, whenever you're ready, you're good to go.
Okay. Yes, you can see my screen now.
Yes.
Yes. Okay, so hello everyone. I'm Nicephore Nicolas, Deputy Sales Director for the Photonics product at Excel, formerly iXblue, and I will briefly present you what solution we can provide for quantum space communication. So just a few words before diving into the subject about iXblue and the Excel. So following the acquisition of iXblue by Groupe Gorgé, end of September, the two biggest entity of Groupe Gorgé, EK Group and iXblue, decided to join forces and become just one brand called Excel, which makes a global industrial high-tech champion with more than 1,500 employees and 250 million euro turnover. And all activities are spread in France with about 20 different industrial sites. So this group is doing many things, from robotics to photonics, and of course I will talk today only about the photonics part of that. So for the photonics market, we have products ranging from components to instruments. All these products are made in-house in 4 different manufacturing facilities spread in France. For components, we offer electro-optics modulators, as well as their matching RF amplifiers, bias controllers. We also have an extensive specialty optical fiber portfolio, from passive fiber for sensing to doped fiber for lasers and amplifiers. I would like to emphasize that we have accumulated a great deal of expertise in delivering space-grade electro-optic modulators, and that we have also a qualified supplier of radiation hardened fibers. In terms of subsystems and turnkey devices, so we have a strong expertise in micro-optics and the passive optics integration. This is coming from a company called Kilia before. We also have some very unique fibers, lasers, very stable for quantum optics. For example, fiber lasers delivering 1 watt at 780 nanometers. And for instruments, we use atom cooling and trapping to build best-in-class absolute gravimeters as well as optical clocks. In terms of, if we go now in quantum communication, just an example, terrestrial example of a CVQKD using a standard telecom component, laser, electro-optic modulators, coherent receivers. So you have the information that will be encoded. The first amplitude modulator to generate is used to generate very short pulses. Second amplitude modulator to use to randomize optical pulse amplitude. And then phase modulator also used to randomize optical pulse. Then on the reception side, you have a 90-degree optical hybrid for coherent detection. Modulators we can provide for this kind of applications. Amplitude modulators, we have specific modulators for each wavelength. We mentioned in the presentation before 1550 or 850 for space applications. Of course, we have modulator for that. And thanks to patented configuration, we can offer very high extension ratio for high pulse contrast, typically in the C-band and also 850. Same thing for phase modulators. Here again, we have waveguide tailored to the operating wavelength, and we have very low insertion loss option for these phase modulators. C-bands, we will be typically below 2 dB. And again, this phase and amplitude modulator are space qualified. Performance of the driver is critical for the generation of a clean optical signal. So we have developed a versatile driver that can be reconfigured to match your needs and can operate as a limiting amplifier for pulse generation, or also as a linear amplifier to generate multi-level signals. For additional components for an efficient coherent transmission, we develop fiber-based light source that is combining expertise in erbium doped fiber and FPGs, fiber back gratings, with extremely low phase noise, less than 0, and also very low line width, less than 0.1 kHz line width. That could be used either as a superspeeder for modulators, or also on the transmission side, that could be used as a local oscillators. As we talk about the receiver side, so we have also some 90-degree optical hybrid with very wide operating wavelength range, excellent dual uniformities, and low insertion loss. And for quantum encryptions, also, we can build some custom micro-optics benches with various elements like delay line interferometers, splitters, isolators, attenuators, and so on. Now, just to give you some highlights about what we are doing today in space environment, from ground to station to geosatellites, we can distinguish two major applications. One is related to the navigation world, okay, so attitude and orbit control system. So we provide a system called iStrix, which is a fiber optic gyroscope from GEO, MEO, and LEO satellites. And also we provide inertial navigation system for launchers. The other activity is laser communication, where we deliver a large range of components, subsystems, and systems. So we start with some 10K reference transmitters and receiver, which are either based for the ground-based station or embedded in an airplane, for example. And we have also a full range of components that could be radar active fibers for low noise amplifiers, boosters, FPGs, micro-optics assemblies. And like that, we can go now up to transceivers, because really the idea in iXblue, now Excel, is to have everything vertically integrated. So we are able to sell components, blocks, and also complete systems. So this is what we can see in this slide, either in navigation or in laser communication. So to summarize, I will say, what can we bring to the quantum space communication? So we have some key optical components for efficient QKD. Could be phase, amplitude modulators, low line width laser, 90-degree hybrid, delay line interferometers. We also have a space-grade version of this component, either from stock on the shelf or also as custom development. And we also have industrial capabilities to integrate space-grade systems based on your design. So what can you do for us, I would say? What are we there today? But first, challenge us with your components or integration system needs. And we are always looking for additional components to integrate in your system, like balanced photodiode, space-grade electronics, for example. So thank you, everyone. And if you have some questions.
Thank you for the great presentation. Is there any question in the audience? Yeah. Martin from Jena-Optronik, please.
Yes. Hello, Nicephore. Thank you very much for the presentation. You had mentioned that your modulators are available in space. Great. So that's good to know, of course. From our experience, the optical fibers can present difficulties when installing on a satellite. So that brings to me the question if you have experience in integrating the modulators directly with the photonic integrated circuits to avoid these fibers.
No, we didn't have this experience. No, we worked a lot also on the fiber itself. So we developed some fibers that are radiation resistant.
Okay, does it answer your question, Martin? Anyone else? Well, if not, in order to stick to our timeline, I'd like to thank Nicephore again for the presentation and introduce the next speaker of the day, who is Malcolm Humphrey, Vice President and the CTO of PLX.
Okay, good morning, everyone, or good afternoon, wherever you are. So my name is Malcolm Humphrey. I'm the Vice President CTO here at PLX Incorporated. So we're a New York company. We're based in Deer Park, and we've been around since the 50s. So we started off as a precision lapping and optics company. We invented hollow retroreflectors back in the 70s. That went on the Apollo-Soyuz project missions. Back in 2000, we invented the monolithic optical structure technology. I'll talk a little bit more about that later. And 2 years ago, we acquired my old startup company called Reflex Imaging, and that resulted in the incorporation of active optical devices with PLX's precision optics technology. So just a brief overview of how this is relevant to quantum communications for satellites. PLX can provide the precision optics necessary for these systems. So we preserve sub-arc second accuracy over some extreme temperature ranges, from cryogenic all the way up to fusion applications. We've recently had an application for a retroreflector within the vacuum area of a fusion reactor, for example. We have various optics, from lateral transfer reflectors, retroreflectors, atomic clocks and delay lines, and the combination of active and passive optics, all incorporated into the monolithic assembly. So this is really relevant for quantum communication, because you obviously need good alignment between the optics. You need a good alignment between the transmit optics and receive optics, and you also need to be able to align the two optical systems between satellites and between the ground stations. So we have a lot of history of doing that for these kind of applications. So one of these I'll briefly talk about. This optic actually went on to the ISAT-2 satellite, which is the LiDAR satellite for measuring the thickness of the ice sheet. So it's part of the Atlas experiment on board. And these two optics allow the transmit laser to be aligned with receive telescope. So what happens is, as you transmit the I can't see my mouse. As you transmit the laser out, small portion of the laser is redirected back into a camera, and that appears as a spot on the camera. For the telescope alignment, there's 4 alignment alignment lasers that are reflected through the telescope, and again are picked off towards the corner of the telescope and fed back into the alignment camera system. So what this allows the overall system to do is align the transmit to and receive to within a few arc seconds over each other, and this survives launch, shock, vibration, and the extremes of space operation, including radiation, temperature, so the thermal radiation from the sun. So this is an active mission. I believe it's been there for the last 4 years, and there is new develop the next version of this, which we are also involved with. Similar kind of mission, laser communication terminal. This was for JAXA. We provided the retroreflector for this system, so a space qualified retroreflector. What this does, it allows the two satellites to optically align to each other. So the one satellite sends out a laser, looks for the retroreflection. Once it's found it, it can adjust itself, and the optical communication can commence. So this again requires, sub-arc second accuracy over a wide temperature range. And again, this is another active mission. Moving on, the PLX's active beam steering technology. This is where the acquisition of reflex imaging comes in. So reflex imaging were founded to make commercial MEMS devices, beam steering devices, and really improve on them with a combination of optics, software, feedback systems, and so on, to deliver a very high level of precision. The original application for this was in optical metrology systems, laser tracking systems, counter UAS, but we also see this as having space applications. So if you want to adjust your outgoing laser to, you've detected where your communication partner is, you can now adjust your outgoing laser to a very high degree of accuracy to hold it on that source or hold it on that satellite. So the MEMS devices have a lot of advantages in this arena. They're very small, they're very light, they're very low power. And the combination of these with PLX's monolithic optical structure technology allows for a very compact, very stable optical subsystem to incorporate it within the satellite structure. And again, all our optics are qualified for space, so we routinely do high level shock, vibration, temperature extremes. So what can you do for us, and what can we do for you? So we're looking for partners to further develop the beam steering technology for space applications. We're looking to do qualification for this, develop new systems for this. We can offer the expertise and precision beam steering, scanning, manipulation using MEMS devices, as well as our existing flight-proven optical systems for bore sighting, retroreflectors, and full stabilized optical subsystems. As I mentioned before, these are qualified through these extreme applications. Okay, so just a very brief overview of all the different optics that we've made, going from very top to left. It was a lateral transfer targeting system for Bradley IBAS ITAS. We have our lateral transfer reflectors. All of these are monolithic structures, so they are thermally matched to ensure that there's no beam deviation with changes in temperature or high temperature gradients. Do a variety of reflectors. On the left-hand side, second down, that was actually that was a lightweight reflector for a late gravitational wave experiment. That was at the end of a 1,500 meter long tunnel as part of an interferometer. And that has a clear aperture of about 60 to 70 centimeters from memory. So it's a very large optic, but also lightweighted and extremely stable. So that's PLX. I hope that was informative, and we can help some of the other companies here with your optical challenges, particularly with stability, accuracy, and those harsh environments. Does anyone have any questions?
It was very informative indeed. Thank you, Malcolm.
Thank
Do
you.
we have any questions in the audience? Yeah, Martin, please go ahead from Jena-Optronik.
Hello, Malcolm. Thank you very much. pointing in the right direction of a laser terminal is very important for quantum communication, obviously.
Absolutely.
But before you point, how do you know where to look at? How do you detect your target?
So with the beam steering, you can actually scan an area of interest. So if you know where your communication partner is within, say, plus or minus 5 degrees, you can scan that area and search for a cooperative target on your target satellite. So if you had a retroreflector mounted on the companion satellite, you can scan for that and look for that returned reflection. Once you have that, you know you're pointing in the right place, you can now commence your communications.
All right, Emmanuel from AUREA, go ahead.
Yeah, thank you for your talk.
You're
I
very
have
welcome.
a question for you because you are an American company, and for example, some of your material can be ITAR, so you can have military or dual-use regulation.
Of course.
About this kind of material. And for the material and for the project you present today, do you have this kind of restriction on regulation?
Many of our optics are dual use and EAR 99. For some of the precision bore sighting optics for military applications, those would be ITARs. The beam steering technology that I'm talking about specifically here is actually dual use. It has commercial applications in industrial metrology as well as the defense applications. So that would be EAR 99. So very much depends on what you're trying to do. But our monolithic structure technology in general is again used for commercial applications. So wouldn't be immediately be ITAR, very likely to be EAR 99. But that's an assessment we'd have to do for every customized system.
Okay, thank you.
No problem.
Any other questions? Yeah, Antonio, go ahead.
Yeah, I was curious, Malcolm, about the challenges you find in the coatings you use in the retroreflector from a fabrication point of view to get to satisfy the requirements of space applications. Which are the main challenges you find?
Typically, it's shock and vibration. It's glass optics. Extreme temperature gradients can cause problems. But what we find is, you know, once the optic is thermally stabilized, it returns back to its original accuracy. So if you have an extreme heat source near the optic, that may cause you performance issues. But again, if it's a constant source, we can actually compensate for that and how we build and test the unit. So, you know, this is something we have done for literally decades. We're very familiar with all the challenges. Our materials are chosen for vacuum compatibility, radiation tolerance, and those extremes of space environments. So we operate from cryogenic temperatures all the way up to, you know, sort of 300 or 400 degrees Celsius. And everything in between, not in one optic, of course, but you know that it's designed for the environment that it will see.
And did you notice evolution in the materials you are using, or you are still using materials from the beginning, let's say?
The materials are chosen for that application. So we have optics in orbit which are still performing, and they've been up there for 15-20 years. So the whole point of our optics is they're monolithic. They do not change over time, temperature, shock and vibration. We call it our plug and play optic because once you fit this within your optical subsystem, you don't need to align it, you don't need to touch it. It's accurate forevermore. So that's why we see the big tier 1 defense companies come back to us time and time again, because they know they can rely on us for these high precision optics.
Yeah, thank you. Thank you very much.
And the very last question from Farzan from Siena. Please go ahead.
Yes. Thank you. Interesting talk. The question I have is with regard to the APT process in acquisition, pointing, tracking. Can you give us, in terms of the timing, how long would it take for you to acquire a satellite, a quantum satellite. And just, I need to know from the time that you start doing your acquisition and pointing and tracking, it's done, both are locked in to start the communication. How long would that take, that process?
It depends on the divergence of the laser, the range, the approximate field of view that you're starting with, but it can be from, hundreds of milliseconds up to maybe 10, 20 seconds. It depends on the area that you're searching. The MEMS mirrors move extremely fast. They have a mechanical bandwidth of kilohertz. So they're able to cover a very large area in a rapid amount of time. So it just very much depends on how many sweeps you do, and that depends on the angles, the divergence, the laser. There's a lot of variables there.
I see. So I'm trying to get some kind of ballpark figure at, let's say, maximum. Your tops, you're looking at, let's say, 20, 30 seconds, something like that.
About that. That's about the worst case I'd expect to see.
Very well. Thank you so much.
All right, and with that, I'd like to pass to the next speaker of the talk today, of our seminar today, Martin Wölz, the product manager in quantum communications from Jena-Optronik. Martin, whenever you're ready.
Hello, thank you very much, Ivan, for the introduction. Can you see my screen?
Yes, the floor is yours.
That's perfect. So let me say one word about Jena-Optronik. We are a world-leading supplier for attitude and orbit control systems. So this is the star sensors that the satellite needs for orientation, but also the rendezvous sensors that the spaceship needs for docking at the ISS, for example, and which is made here. We have in-house electronics manufacturing and test capabilities. Our core expertise is the development of electronics that we take from a laboratory status to an application for space. And so this is the focus here of my talk. We focus on optoelectronic subsystems, and we help to bring technologies from the lab to the satellite reliably. Now, where do we see our engagement in satellite QKD? In order to explain this, I have drawn here a summary of the optical terminal that we see for satellite QKD. So in satellite QKD, the photon source is installed on the satellite. This is typically a prepare and measure source. So the quantum state of single photons is encoded arbitrarily by, let's say, polarization. One way of doing this is to install individual lasers, VCSELs, for example, and to give them individual polarization and then turn them on or off. And another way of doing this, a parallel activity, if you like, is to have only one laser source and then by ways of beam splitters, separate the light path, modify the light properties, and then turn them on or off with electro-optical modulators. So these are the two competing solutions for single photon sources or faint pulse sources that you need to approximate single photon sources. The whole single photon data stream needs to be supplied with random numbers in order to be unpredictable and to perform the key distribution. So then this photon stream goes to Earth via a telescope, which is also an important part of the satellite, of course. Now, we've heard from AUREA that there are other approaches. You can construct a QKD system by way of entangled photons. If you do that, you have the entanglement source on board the satellite, and you need two telescopes. Unless, and this has been proposed by some people for GeoQKD, for example, unless you store one of the branches on board of the satellite. And then, of course, you need a single photon time-taking electronics to record what would have been sent on this branch here, and then to digest it and make the satellite the Alice, or to transmit it at a later point with a prepared measure source. In addition to that, there also need to be classical optical communication channels installed, and they have to be fed via an optical bench, have to be fed into the satellites. Now, what does Jena-Optronik do in this context? I'll give you an example here, how we work on a single photon time-taking electronics. In this case, an electronics was desired that can resolve single photon events with a resolution in the order of tens of picoseconds and with a data rate in the order of hundreds of megacounts. And of course, it has to be radiation hard in order to support satellite operation. Such a device today cannot be bought anywhere. There is no mass market, so there is no commercial device. Yeah? There are a few similar devices that have been developed for accelerator physics, but there's nothing that fulfills these specifications. So we are part of the Q-Source project. This is a German government-funded project together with other institutes and companies, where our role is to develop a custom time-to-digital conversion ASIC, which will fulfill these specifications. So this is we're in the process of performing gate-level simulations of the logic in the circuit, and then this will be cast into silicon, and we expect to have a breadboard ready in next year. This is an example of how we approach challenges for satellite electronics at a very fundamental level, and that's how we hope to support laboratories intending to bring QKD onto satellites. The roadmap that we see is shown here. The two satellites that are known to date to perform QKD have been mentioned by Laurent from Thales already. This is the Chinese mission from 2016 and the Jena-1 mission that has just been launched. Now we are looking at a few European and Canadian and one mission from Singapore here that are scheduled for the next years, which are experimental missions. And we estimate that deployment of the European satellite constellation for QKD will start in 2026. We want to be part of that, and in order to do so, we are working on developing with partner institutes a VCSEL-based faint pulse source, which is at TRL5 roughly at the moment, and which has to be at TRL9 in order to fly on the constellation. In connection with that, we will need the quantum random number generator. There are QRNG systems out that work on fiber systems, and the challenge will be to qualify these for operation in space, and we think that we can combine this with the VCSEL SPS development. On another note, we have the modulator driver development. As I said, this is an alternative solution, and we will hear more about this in the next talk. The modulator needs a space-proof driving electronics. We've heard from iXblue and from Nicephore that they provide these modulators, and Jena-Optronik intends to engage in an electronics driver development here. And then we expect that within 2 years from now, roughly, this can be the base for single photon sources used on satellites. We have the time-taking project going on that I just mentioned before. Now, to summarize, in our point of view, where is my screen? It's gone. Too bad. My screen is gone. I'll bring it back, my screen. So, to summarize, in our point of view, satellite QKD is moving actually out of the lab and into the industrialization. The subsystems that Jena-Optronik is working on are the QRNG, the VCSEL source, the modulator driver, and the single photon time tagging. We are, of course, looking for new input and new ideas here. We see ourselves as the electronics developers and the enablers for laboratory technologies, and we see a few gaps. For example, there is a concern of the polarization stability, and to my knowledge, at the moment, there is no very practical solution for active polarization control on board a satellite. Yeah? The only thing that I have seen is a motorized version with a 1/4 wave plates, and that is something that you actually want to avoid on a satellite. So we are looking for more intelligent solutions there. The timelines are very critical. We've seen that the constellation is about to be deployed from 2026, and that means we are in a real hurry. And of course, our solution is to use the expertise that there already is in the industry to accelerate these developments through space. With that, I thank you, and the talk is open for questions.
Yeah, thank you very much, Martin. Is there any question in the audience?
Yes, I have a question for you, Martin. So you are developing both entangled sources and prepare and measure sources? Is that it?
We are electronics developers, not photon source developers.
Okay.
So the entanglement source is out of our area of expertise. But if the entanglement source people want to record their data in space, then they need single photon time tagging electronics, and this is something we can support.
Okay, and do you also develop electronics for detectors, onboard detectors? If we assume, yeah, because as you know, there is some architectures where single photon detectors are on board. So typically APD, avalanche photodiode, and that require also electronics for this. So you can develop this electronics for single photodetectors.
The Q-source project that's going on at the moment starts after the detector, because we feel that the detector itself has to be integrated with the optics, and that's out of our area of responsibility. But the electronic signal processing is something that we are about to do. The actual Q-source project has the objective to develop a setup for QKD with encoding of angular orbital moment. But in the end, this only translates to your mirror and channel setup. And in this particular case, 8 channels are required. We should get more in detail about this. In principle, we could extend our circuit to a little bit closer to the APD.
Okay, and the time tagging also is in your area of expertise?
The time tagging is what we do within this Q-source project. Okay. The time tagging is the government-funded activity where we develop the application-specific circuit, which is not commercial and could not be developed if there was not the research funding for this.
Okay, and you have contractors for the space environment testing, like radiation, vibrations, shocks. You are not doing these tests in Jena-Optronik, no?
Vibration, a thermal vacuum we do in-house. Shock and radiation we outsource.
Okay. Thanks.
All right, Farzan from Siena, please, your question.
Yes, thank you. A question I have, you mentioned about the polarization compensation. Can you give us some idea about the requirement for that and the order of magnitude or the scale of these polarization fluctuations? Is it, and the source, are you talking about the polarization fluctuations in atmosphere? Are you talking about polarization fluctuations because of the vibration on satellite? Could you please elaborate on this?
Yes and no. the request has been brought to us by our system partners. As I say, we are experts in electronics, not in optics in this sense. But the satellite is always subject to thermal fluctuations, for example, and it can also be subject to mechanical stress. And if you have a modulator setup, for example, where the light is transmitted by fibers, then these fibers are very susceptible to mechanical deformation or mechanical tension, for example. So it may be useful to integrate active polarization correction on board the satellite. And I have actually followed the literature a little bit, and there are, for example, approaches that employ liquid crystal on matter surfaces. And this is something that is actually commercial for holographic screen projection. If this works, maybe one could also adopt it to satellites. But this is a very this is a pure speculation from my part, and we are looking for input there. Maybe one of you has an idea of how to go about this problem, and then we would like to see if we can help with the electronics needed.
Very well. So my understanding is that based on what you described, the main source of polarization fluctuation is the vibration in the satellite as a platform, right? Is that what the source of this is?
Yes.
Okay, very well. Thank you so much.
Yeah, I really like how many discussions come out of the questions today. If there is no other question for Martin, I'd like to pass to the last speaker of the day, who is Costantino Agnesi, a scientist and a product developer from ThinkQuantum. Costantino?
Okay, can you see my screen?
Yes.
Perfect. So I would like to start by thanking EPIC for organizing this excellent meeting, very interesting so far. So I will begin my talk spending a few words on who we are, who is ThinkQuantum. So ThinkQuantum is an innovative startup and spin-off of the University of Padova. And we offer solutions, cybersecurity solutions based on optical and quantum technologies. And in ThinkQuantum, we aim at covering the full value chain. That means we develop and manufacture quantum key distribution and quantum random number generation systems. And we are also able to design any tailored solutions for our customers. ThinkQuantum is fully Italian with an Italian shareholder structure. And we are able to offer a reliable European supply chain to all of our partners that might have any geopolitical sensitive applications. So how is ThinkQuantum established? Basically, we have two main partners. On one side, we have Officina Stellare, which is our major industrial partner. And Officina Stellare is a well-established company that is listed in the stock market here in Italy with a solid international network and reputation. And this is because it offers a large portfolio of telescopes and telescope mounts for a large number of applications, both for ground and satellite applications, ranging from celestial observation, Earth observation, and laser communications. Then, as the scientific pillar of ThinkQuantum, we have the University of Padova. And this is because ThinkQuantum is recognized as a spin-off of the university, which grants us access to resources such as labs and all the relevant industrial and intellectual property of the University of Padova. Furthermore, we have our two co-founders, Professor Paolo Villoresi, which is the president of ThinkQuantum, and Professor Giuseppe Vallone, which is our chief technical officer. Both of them have over 20 years of experience with several prestigious international positions within the scientific community. So together, we are able to offer interesting expertise in the field of satellite-based quantum communications. In fact, as a spin-off of the University of Padova, ThinkQuantum is backed by over 20 years of research in the field of satellite quantum communications. And thanks to our co-founder, which is a premium provider of optical systems for ground and space applications, we are capable of offering satellite payloads and ground segments for quantum communication systems. In fact, our offer is both in the space segment and in the ground segment. And our offer has a secure design because we have several patents that secure and demonstrate the reliability of our design. We have a flexibility because we're able to offer tailored solutions to our customers in terms of wavelength, system interfaces, footprint, etc. And as I mentioned before, we're fully based in Italy. So this means that we have an European supply chain. Regarding the optical ground station, we offer the development of optical ground stations that are able of receiving and decoding the transmitted quantum states from the satellite. And we do this with a large flexibility in the choice of the telescope. And this is mainly due to our industrial partner, Officina Stellare, which basically gives us a large portfolio of telescopes to choose among. And furthermore, we have the service to adapt any existing optical ground stations to the requirements of quantum communications. And here we leverage on our pioneering work in satellite quantum communications. In fact, our president, Professor Paolo Villoresi, back in 2008, demonstrated the first exchange between a satellite and a optical ground station back in 2008. And this was done in collaboration with Professor Anton Zeilinger, which just recently won the Nobel Prize. So this is something, a point of pride of our company, being really pioneers of this sector. And then we also offer services in the satellite payload development. And this also comes from our expertise and as our inheritance from the University of Padua. We are able to offer quantum random number generators that offer the highest levels of security for the generation of random numbers. And also we are able to offer quantum state generators with a patented technology that offers very high qualities in terms of robustness, reliability, and compatibility with standard quantum key distribution protocols, such as BB84. In fact, at the heart of our polarization, our quantum key distribution system is the Hyponiac polarization encoder. And here you can see a scheme of how it works. And among its key features is that it is fully secure against side channel attacks. This is something that not all encoders can say. For example, the solution of having multiple lasers, one for each different polarization state being sent, can suffer from side channels because each laser can have a different optical response, can have a different wavelength. And so it can have different characteristics that can be used by an attacker to gain information about the quantum state being sent. Instead, the Hyponiac being based on a single laser and then modulating these laser pulses into the different polarization states is immune against these type of attacks. Also, the Hyponiac has a self-compensating design. This means that it is fully immune to temperature and DC drifts. Its design also allows us to say it's fully recalibration free, meaning that once that it's been installed, it will not need any further recalibration, which is an excellent characteristic for satellite missions. It offers an extremely low quantum bit error rate. In fact, our scientific paper where we introduced this technology still holds the record as the lowest intrinsic quantum bit error rate ever recorded for any quantum key distribution source. And the other two features is that it outputs a stable and well-defined output polarization states. And this, just coming back to the point of Martin, this has a fully free space output, meaning that it does not couple the light into a single mode fiber. So to work with the Hyponiac, you don't need any correction system for the polarization fluctuations that might arise from using a fiber-based design. And currently in ThinkQuantum, we are working a space-qualified version of the Hyponiac. And this is because we really find that this polarization modulator is a great solution for any space mission. In fact, this design has been awarded by the Italian Ministry of Education as the best public research of the year just recently. And here you can see our Pino Vallone, Professor Giuseppe Vallone, who is our Chief Technical Officer, receiving the award from I think the Minister of Education in Italy. And well, the iPoniac has been a technology that we have tested quite thoroughly. We have tested it in free space links, and this here you can see basically the record-setting quantum bit error rate that we obtained with the iPoniac. And a key feature is not only the low level of quantum bit error rate that we obtained, but also the stability of the quantum bit error rate that we obtained. For over 14 hours. We maintained a quantum bit error rate of under 0.2%. We also have tested this in buried fibers. So we have worked with the iPoniac polarization modulator in fiber-based systems. And in fact, with this, we have developed our turnkey solutions, and the iPoniac is at the heart of our QKey, which is our QKD system. And we also have a quantum random number generation that we call ThinkQuantum. And well, these solutions for now have been fully tested and are turnkey, and we offer them commercially for data centers. But it's in ThinkQuantum's interest to develop these same products into something that can be easily installed into a satellite. So yeah, this is about it. And I thank you again for having me here.
All right. Thank you very much for this encouraging talk. Do we have any questions in the audience? Please go ahead. I was wondering, so you mentioned, of course, installing the systems on the satellite. What is the typical weight of these systems for quantum random generation and for quantum key distribution?
Well, it's not really heavy. The thing we have, we use the standard of, it's called the, how are they called? Rack mount units. Those are, we basically have a supplier of these rack mount enclosures, and the rack mount enclosure is much heavier than the optical system that we have inside. So basically the weights that we declare on our data sheet are dominated by the enclosure, not by the optical system that we have inside. So basically, I would say that we can go for very small, very compact designs. As University of Padova, we have had some more research-oriented projects where we demonstrated that our design can basically fit in a CubeSat, so basically a very small enclosure, both in size and in weight requirements. So basically, I can't give you a number, because basically the number that I could tell you is the number for a rack mount system, but that would be fully that wouldn't be the exact number that you would need to allocate for a satellite mission, because obviously you don't need the enclosure in a satellite. You can do a more customized enclosure for it.
Sure. I understand. There is actually a question coming now from Thales Alenia Space. Laurent, please.
Yes, hello, thank you for your talk. Just one question. So do you also develop this kind of QKD rack solution for entanglement for BBM 92 protocol? Or?
So we still don't have any product in the market for this, but we are interested in the development of this. And this is something that we have been analyzing together with your Italian, I wouldn't know if are your brothers or cousins of Thales Alenia Space Italy. We have definitely discussed the possibility of developing entanglement-based solutions based on our IP.
Okay. Yeah, greetings to Paolo and Pino, by the way. Thank you.
Great. Is there any other question? I think our seminar is coming to the end. So this is the last opportunity. Okay, Martin, please, from Jena-Optronik.
Laurent has just raised the question about entanglement, and we've heard a comment from Costantino. Maybe any one of you can answer, or maybe Emmanuel, you can help. When we talk about entanglement satellite QKD, then the data rates are significantly lower than the prepare and measure data rates. So I am assuming this has to do with the physical process of the spontaneous down conversion. Maybe Emmanuel, can you state where the limit for the data rate is and what emerging concepts there are to go beyond that?
So the limit for the data rate is mainly due to the material, so to the detection itself, and more especially to the jitter of the detectors. So if you improve the jitter of the detectors and the time resolution of the system, you can increase and you can improve, I think, the data rate of the system. Maybe Laurent, you can confirm that.
Yes, and I also can add that the problem is that you have two channels, and you should have the visibility of the two channels at the same time.
Yes.
And so that's the problem when the satellite passes above two stations. So the two channels should be available, and the problem is that you have also double the losses. So typically you have for low Earth orbit like ISS, for instance, so it's 400 kilometers, you have roughly 30 dBs of losses in each channels. So that means 60 dBs. So one way to speed up, to increase the performance of the system is indeed to increase the number of pairs emitted each second. And there is a limitation in the spontaneous down conversion, parametric down conversion process. And for sure, what Emmanuel just said, if you have lower losses, there is also the problem. So the detectors should be able to detect, to have a rate close to the emitter. Otherwise, the emitter will emit more pairs of photons per second than what can detect the detector. So that's the problem. And the jitter of the detector is also a problem. If you emit too many photons per second, then the jitter of the detectors does not allow at some point to detect which pairs of photons you have detected. You're lost. You cannot distinguish. Yeah, you cannot distinguish the photons that is emitted, and so you cannot perform QKD. So, but yes, so why should we use entanglement photon source for QKD? Because in fact, that's practical because you do not store cryptographic material on board. So it's not a trusted node. So that's very important. And if you want to perform quantum information networks, these networks are based with entanglement resource, entangled photon pair resource. And so you definitely need to use entanglement. For quantum information network, you need entanglement. So you need an entanglement source on board. But for QKD, this is a trade-off. Should we use an entanglement source or not? A prepare measure and prepare measure source. And the conclusion of what I've performed the Chinese is that you have a much bigger QKD rate when using a prepare measure source. And so for QKD, it's easier and more practical. But the problem is that okay, I can discuss this topic 1 hour. So I will just say that entanglement is definitely needed for quantum information network. And that's also a good point if you do not want to store cryptographic material on board. If you do not want to have a trusted node, the satellite trusted node, then you need entanglement source.
All right, great input, Laurent. I suggest that we move this discussion to the informal ramp session after we close this public event. So let me just share a quick presentation with you. So unfortunately, our online event is coming to an end. So we had the pleasure to welcome 6 speakers today from Thales Alenia Space, from AUREA Technology, from iXblue, the PLX, Jena-Optronik, and from ThinkQuantum. This was a great discussion we held today, and I invite you to follow more of such events in the series of online technology meetings presented by European Photonic Industry Consortium. You can see now the list of the upcoming events until the 2023. I will just highlight a few of the events that might be of interest to this audience. So on November 14th, 15th, we have an offline technology meeting that is coincident with the Electronica show in Munich. And it's called the Two Sides of One Coin of Photonics and Electronics. In November 21 and 28, we have online technology meetings dedicated to peak packaging and testing, and as well to Earth observation. And in January 9th, the first OTM of the upcoming year will be dedicated to metamaterials and meta lenses. I'd like to thank also my team with the EPIC Photonic, the EPIC European Photonic Industry Consortium supports you in looking for technologies, market reporting, networking, access to new markets, mentorships, HR support, and investment. And I'd also like to thank the sponsors of today's event, ficontec, PLX, and EuRA. And with this, I'd like to close the event. Thank you for your attention.